Today's speaker is Yunyan Zhu. He's an assistant professor at the School of Computer Science at Carnegie Mellon University. Before joining CMU, he was doing postdoc at MIT, and also he served as a research scientist at Adobe Research. He did his PhD at UC Berkeley with Alyosha Efros. And his background is basically computer vision, computer graphic, and computational photography. He's kind of leader of many papers in image synthesis, basically. Starting from cycle-GAN, I'm sure a lot of you are familiar with cycle-GAN, and many more papers on GANs. So today's talk is about human-in-the-loop model creations. Yunyan, thanks for accepting my invitation. Floor is yours. You can start.
Yes, thanks for a nice introduction. Today I will talk about some recent work on human-in-the-loop model creation. So just give you some context of the work. So machine learning has revolutionized content creation, which allows us to create new images in different ways. There are a bunch of here are just a very small sample of the great work people are doing, including some of our own work and some other works from the community. Let's give you several examples. We had this work with Philippe Sola et al. And on this text-to-pic, which you can create a cat by a simple cat join. Like here's another cat, and here's how the interface works. So this machine learning model can translate your sketch into a cat photo in real time. Here are more interesting cats we have created. Another more recent example is the GAN system, which allow you to create a semantic label map, like whether this is a mountain pixel or this is a sea pixel or sky pixel, and it can create image in real time and pretty high resolution images. And we show this demo in front of thousands of audience. And this you can also download it from NVIDIA's website called Canvas, which you can use on your laptop. So yeah, a more recent example is this work called swapping autoencoder. And so the idea here is we can try to generate image from different seasons or from different daytime, nighttime, and this will allow you to swap the style between two images. So you can this feature has already been integrated into Photoshop 2022. So if you download the latest Photoshop, you can find a filter called landscape mixer. So you can do that just on the Photoshop, and you can choose different slider and choose different reference images. So these tools have been available on lots of different kind of consumer applications. So the good news is the data plus machine learning it seems to be very powerful, as you can just use the same algorithm on same algorithm on different types of data, and you can produce different kind of applications. But there are still kind of big issue here is to train a model. Of course, you need to design a model into like the loss function. You need to have some GPUs. But most importantly, you also need to collect a data set. So if you look at the data set we only have a few data sets, maybe 5 to 10 data sets. People are working on for training unconditional GAN models. So for sure, we have data sets for other applications as well. But just for unconditional GAN, we have a few data sets. But that's a small portion of the images we are dealing with. Maybe we are dealing with some real cases which are interesting, but that's not that common can be collected as a data set. Maybe I'm interested in my own photos. I'm interested in not a generic cat or dog. I'm interested in my cat or dog, or my friends, the pictures I have taken. Or maybe I'm interested in other kind of random images. So we can argue that the natural images, in our visual world is much larger than the data sets we can collect. A more important question here is it's still a very small portion of all the images a human can imagine. For example, if you want to use generative model to create a movie, like this is a kind of very cute baby Yoda. Um, the audio is not that important. But so basically, if you want to create a movie, then you can't just collect training images, right? Because that movie does not exist. If you can collect training images of the movie, uh, that might be the movie was already done, right? So that was less interesting. Or you want to create a new game, another game I was playing before. Um, so if you want to design a new game using a generative model in one day, but you don't have the kind of visual results of this game. Otherwise, you don't need this generative model to do that. So the chicken and egg problem is to train a generative model, we need to collect images, but to create new effects, we do not have that images. Although that was a very difficult issue to tackle with. So one thing we can do is if you consider how humans interact with the models, we have some ideas and we collect a data set, and then we collect a training data set. Step two is we train the model with some GPUs, and then step three is so then once we train the model, what can we do, right? We can maybe one thing we can do is we can choose a snapshot. We can choose a particular iteration we like to use. Or maybe we can do something else. We can maybe change the hyperparameters, maybe change some lambda a little bit. Maybe to change the effect of this model, what this model can generate, we have to recollect the data set. We have to add more images, maybe remove some images, maybe do some pre-processing, maybe align the faces, a bunch of things we can do. But most of the time, people interact with models through a data set. You need to, if you want to create a model which can realize your idea, you have to collect a data set which can realize your ideas, or which, as mentioned before, is extremely difficult. Okay. By the way, stop me anytime if you have any questions. One thing we can do, which people are doing, is maybe we can, instead of collecting a large scale data set, we can collect a very small scale data set. We can collect a small set of training images. So instead of collecting a million of images, 70,000 images, we can collect maybe 2,000 images, maybe 100 images. So that can reduce the cost of this interaction, right? So each time when you interact with the model, you only need to collect like hundreds of images rather than millions of images. That's one way to make humans' life easier and to iterate the idea faster. Right? So so the idea is that this data is expensive, and to train the model, we need to not only collect the images, but also need to filter the images. We need to process the images with align their faces. And it often takes months to years to prepare this data set. And that's not scalable if anyone wants to create a generative model just by themselves. The issue is, you may ask, oh, why not we just use less data, right? With like fewer images, like let's instead of using 70,000, we use 1,000, or maybe it's 100. The issue here is if you train a GAN model on standard on like 100 photos like Obama, it just doesn't work. It doesn't look very nice. You train a model on 160 cats. It doesn't look very nice. So you can train a model on fewer images, but they just don't work. But if something is not working, we want to ask why, right? Why it's not working? Is that the issue of the generator? Is that the issue of the discriminator? Is that some loss function has some issues? So one thing we are looking at is this discriminator overfitting kind of plot. This was I believe this was original. The idea of looking at discriminators overfitting is original from the Big GAN paper. So if you want to take one lesson from this talk, maybe when you train GANs, you should look at whether discriminator overfits or not. That's very important in metrics, more important than FID. So one thing is we look at the training accuracy, and we look at the validation accuracy. The training accuracy means, yes, the validation accuracy means we have a holdout test set, which we haven't trained the discriminator on these real images. So you if you have 100% CFA data, it looks fine. But let's say if you if you have like 20% CFA data, so the discriminator will not work on the validation set. Basically, the discriminator will not work. Even your training loss is perfectly fine, but in practice, discriminators does not work for new images. So an overfitting. And the issue here is if you look at the FID plot, which we don't show here, at this particular moment, the FID just explodes. And the same idea, which are more extreme, yes, you can look at 10% of data. So if you look at this one, and then suddenly it just doesn't work. And we'll stop here because the model has exploded. It's modeled FID because of 200 or 300, something like that. So yeah, one thing you would like to really monitor your GAN training is to look at how discriminator overfits and how they work for the new images. So now we identify one of the issues could be the discriminator is severely overfitting for if we don't have enough data. And one thing which computer vision people always do if for overfitting, yes, just to apply some data augmentation. You just it's a kind of cheap way to collect all the data. You just create 10 or 20 different copies of the same data, and so this can enlarge your data set by a large margin. So that's everybody is doing that for classifier training. So we can also do it for GANs. And so the question is how to augment GANs. This was a paper in collaboration with Shen Yu and Songhai's group. And so the idea here is what previous people have tried is you can apply this transformation, geometry transformation key to the real images. And the issue here is if you apply a particular jittering or cropping, your generative image will also create these kind of artifacts. If you apply cutout, your generative image will also get cutout artifacts. So the issue here is so before, when people apply the augmentation to images, the images are the input of the system. Now the image was the output of the system. So if you apply any kind of augmentation, new output will carry this kind of augmentation. So that doesn't work. And people have tried that before. They mentioned in a paper that the augmentation doesn't help because of this, precisely because of this issue. And so one thing we can do is, okay, so maybe we can apply it to both the generated images and the real images, and then maybe they can cancel each other. That looks nice. But the issue here is, if you apply to the discriminator, but you don't apply to the generator, the model will have very low accuracy on the generated images. It will have high accuracy on the augmented generated images. So that's the issue here. The reason for that is that this generator is not involved in these augmentation games. So in our paper, we apply it just everywhere to the discriminator, real and fake, to the generator as well. And to make this work, we need to make this transformation layer differentiable because we want to get gradients from the discriminator through this layer back to the generator. If that makes sense to you. So this makes results much better. We apply three types of augmentation, like color jittering, translation, and cutout. You can also do translation more like a cropping, but without scaling, without changing the scale. So yeah, just by and once we apply the augmentation, we can also get the ingredients from the discriminator through these augmentation layers to the generator. So and using this method, we can achieve pretty nice results. The gray bar is the Staugen to baseline, and the red bar is applied differentiable augmentation. It helps a lot if you have like only 10% of data, and it can make the performance degrade much more slowly compared to the baseline. And we also show some results on applying this differentiable augmentation to big GAN model. So you can apply to any kind of model. You can reduce the FID by half in the 25% training data. And here are some samples.
Okay. Union, I have a question.
Yeah.
I just remember I've seen another paper from NVIDIA. It's called training GAN with limited data. I think they also use this transformation to output of the generator and the real data. How this work is different from that work?
It's quite similar. It's kind of concurrent work. I think they have a. We'll talk about in a minute. We'll talk about some other works in augmentation. They are quite similar, but yeah, we were like, oh, this idea must work because other great researchers also have similar ideas. So that's very interesting to know. Yeah. Okay. Yeah, we'll see it in 2 slides. So we compare it to the low shot generation, which will have 100 images, and it can improve the results significantly. To test whether generated or fitting or not, we also show some interpretation results was trained on 100 images. And this code is very easy to use. If you go to the website or to the GitHub, you can just import the diff augment, and whatever you are doing before, just add diff augment to your data, and that's it. So you only need to make 3 lines of changes. You don't have to do anything more significant than that. So just apply it to the discrimination, real and fake, and apply to the generator. Just 3 times. You need 3 lines of code. Okay. Yeah, this is actually define the policy using a text string. Okay. Yeah, we talk about this just as you mentioned before. We see a bunch of people around the same time, maybe around the same month, maybe around the same two weeks. People working, having all these ideas about using augmentation for GANs, and we are only one of the 4 papers. I've seen different papers focus on different aspects. In the Style in the NVIDIA paper, they focus on the adaptive policy, which they can turn the augmentation ratio in real time. And some other paper, like this paper, Google paper, focus on different types of augmentations and how they affect the performance. The different paper focus on different things. Our paper also focus on the few shot, low shot learning, which some people don't. But I think I urge you to look at all of them, and they have some all kind of different small differences. But the important idea is we need augmentation if we don't have enough data. Okay. So far we talk about still talk about interaction with models. Maybe we can use small training data, and it can make our life easier. Like if you try some idea, or you want to have a model to generate paintings, so you don't need like 10,000 paintings, only 100 paintings. But that still doesn't solve the issue, which how can we train a model without training images, right? If I have some idea, I want to make a movie, or I want to put myself into a movie, I have this idea about but we don't have that images. So we don't even have a single image. Maybe we have 1 image or 2 images. So the existing method is promising, but still doesn't fit for this particular purpose. So one thing we can do is we need to rethink how we interact with the models. Maybe we can talk to the model directly without going through this collection, like data curation process. Maybe there are better way to interact with model. We can talk, kind of ask model what we want to do without collecting a training set. And so the idea is, how can we directly connect our imagination to generative models? So we need some kind of intermediate media which are beyond collecting the training images. So one way to collect someone's mind to the visual data is to use sketch interface. Here is a very famous work in Sigua 1999 by Takeya Igarashi called Teddy system, which it's pretty cool. Even in today's standard, they just draw a sketch and they can create a 3D model which looks like that sketch. That's like 20 years ago. And we also some other recent work, other work like sketch the photo, you draw a sketch, you create a photo. That's all before deep learning. So the idea is, can we create a generative model just by human sketches? We draw what we like to create, and our model can listen to our kind of sketch input and create a model accordingly. So here is a recent work in collaboration with Shen and David. And so here is a pre-trained model, like a pre-trained model. Here are some random samples from the model in our horses, and then we can. The idea is the user can provide 1 or maybe 3 or 4 sketches, and then we can create a new model, GParm, which can generate samples which look like the shape or the pose of the input sketches, while still preserving the color and texture and the background of the original images. Okay, so here we propose a very naive algorithm to do it, but it works reasonably well. So we just present it. So here's a model we like to train, and then we extract some kind of contours using a photo to sketch network, and we'll compare it with the user sketch. We also need to apply some augmentation here because we only have a few sketches. And then we also have a second, this is capture whether the image resembles the sketch or not. And we'll have a second discriminator, which captures whether the output is a horse or not, because we still want to generate horse. We still want to generate a realistic horse, right? So have a second discriminator which capture whether this is a horse or not. And optionally, you can also have a weighted regression. You want to penalize the large change from the weight space from the original model. So this works worse than this one, but the advantage of this one is it does not need the access to the original training set. So this one requires you to have access to the original training set. So it depends whether you have the original training set or not. And so we just train this model, and this network are all fixed. Okay, and here are some results. Here the sketch input, and here are some samples where we see 30 sketch inputs just to test the algorithm. Here are like 30 sketch inputs, but this is more like a contours created by the algorithm. These are not real user sketch. So the more exciting thing is how this method works for a single human sketch. Here are some results. Here the single sketch, and it works less well, but still kind of most time it kind of works. And here another one from the cats. Interesting is once you have the model, you can just do whatever you want with the generative model as you did before, right? It's just for example, you can do interpolation between 2 images with these new models. Okay, you can edit the images with these new models. Like you can find some latent space using GAN space. You can edit a photo. But this is just like any kind of generative model you have created. It's nothing. You just create it using sketching rather than collecting data set. And there are other ways of interacting with the model. For example, when we like to create a model which have trees on top of this tower, but the issue here is we only have 1 or 2 images about this particular interesting phenomenon. So if we would want to do it the same thing for the image, we can just open a software and then copy and paste a tree on top of the tower and maybe do some blending. So we try to do the same thing for the model, for the generator. Is we would like to modify the weights of the generator so that we can create new samples. For example, here's the original samples. We like to create new samples with trees on top of the towers. So that's the idea. And here how the interface works. So here, this is here are some like image viewer. And this is you can choose which location you want to edit, and you want to choose which audio you want to paste. So let's look at how it works. Here are some random samples from the stock and truth. These are fake samples. These are not real images. And then you can annotate 3 or 4 places you want to annotate the tower. And then you can show like how you can find similar features in other images. So we only annotated a pointy tower. We're not annotate every single roof, just this particular shape. And then you can choose, you can grab a tree. For example, you can grab a tree. And you can paste this tree on this particular place. Okay. And then you can modify the weights. It takes about 10 seconds to change the weights of the network to achieve this new computational purpose. This is before, this is after. And then, let me talk about the algorithm before I show you more examples. So here is a very simple algorithm. You can think about we're only editing a single layer here. And this layer is called W0. It inputs, if it's a convolutional feature map, if you look at one location, it's a 5-dimensional vector, for example. And then it produces 256 output channels, but the convolutional kernel is also 3x3. So for example, maybe some keys, some input keys correspond to the tower features. And then you produce the output, and you can shape it into a 3x3. So the idea is, in a normal generator, if you feed some tower input features, it should produce tower output features, right? And then you render it, it looks like the tower. And one thing we can do is we can hijack this model, and then we can replace the tower output features by a tree output features. So that's the idea. So we try to remap a tower input feature to a tree output feature. So it's as simple as that. I think we are the one who selected these features, so we know what the features basically are generated images. We know we have all the intermediate features in the generator. Okay, so the idea is if you look at it as a linear case, let's try to make it simple and just work through a linear case, right? So in a linear case, if you say, oh, basically I have a bunch of input features, I have a bunch of output features, I try to learn a weight W. This is what you can learn. And then, so this model rewriting operation is just saying, I want to minimize the input-output mapping. Why? I want to enforce a new constraint, which I want to map a tower input features to a tree output features. That's a new constraint I have, but I still want to keep my original. I want still want to map sky to sky. I want to map door to door. I don't want to change anything else. I want to keep my original kind of mapping, but add a new hard constraint. And if you work out the math, it's just a constraint least square. I will skip some method. So the idea here is the difference between the old weights and new weights are just this particular term. This C is the covariance matrix of the input features, and this K star is the input feature we like to enforce, and this lambda is also it's a vector matrix. It's a rank 1 update. So the interesting part is you can actually pre-compute the C. C is just you sample some input features, input vectors, and can pre-compute the C. This has nothing to do with the UI. You can pre-compute it before you load the UI. Okay. And so if you plug this solution back to the constraint optimization problem, yes, in the network we also have a bunch of other things like a radio, like batch norm, like maybe some other layers. So we can express this as a non-linear function f, and we plug in these linear solutions, and this case study is known. So we only need to optimize this capital lambda. So this is, for example, this is a 512-dimensional vector. So the entire optimization problem is to try to find the optimal 512-dimensional vector, which give us these rank 1 updates. And once you get this direction, you can you can update the weights again using this pre-computed direction. So the idea here is we want to do as minimal as possible. We don't want to change the entire network. Otherwise, you will also change the sky. We also change the. So that's the idea. Okay. Yeah. So basically, the idea here is we just pre-compute these directions and we optimize this lambda along these directions, and then we update the weights. So that's why it's so fast, because it's instead of optimizing millions of parameters, we're only optimizing like 5 12-dimensional vectors. Okay. And here we show more example. Here is you can see some faces, and then you can annotate, for example, the mouth region, and then you can grab a smiling kind of TC smile, and then paste that to the model. Another more interesting example is you can annotate the eyebrow region of kids. You need to use 3 or 4 annotation, and then you can grab this mustache from this man and paste to the kid's eyebrow. And so this is actually a very interesting editing, because this is very specific. It only applies to the kids. It does not apply to, does not affect adults. And also very general, because it works for any kids, or for many different kids, not only for these 4 kids we annotated. Another example on horses is we can, here are some samples from horse, and then we can see, we can annotate some, we can annotate the head of the horse. And then we can add a head to the horse. So the idea here is we would like to just editing the models, and this operation is does not only apply to GANs or VAEs. It can apply to any kind of model which can produce images. For example, we apply this idea to the NeRF model, which NeRF is training on multiple views and try to create new views. We have a model called conditional NeRF, which can produce samples of different chairs. So the idea here is we have a model which this model is have both the shape code and the color code, and each shape code and color code affects the shape and color of the chair. And here the idea here is we can modify certain layers for shape editing and certain layers for the color editing. And this will allow us to change the NeRF weights based on the user's edits. Okay, and then here is our interface. Here, show some examples. Here are some different views of the same NeRF model. And here is we can choose a color. And here you can also choose the background color. And now you can render the image from different views. The same idea here. You can choose a view, and then you can decide to remove parts of the objects using this shape brush. And then you can update the weights of the NeRF. And you can render it from different viewpoints. So the edit is viewpoint consistent. The same idea here. You can also swap the style and the color
it can transfer the color from different instance to this particular so far. And you can propagate these edits in the weight space. So here are some additional examples on cars. And the scribble does not have to be very precise. It does not have to be a precise computation, but the NeRF learns to propagate this scribble into the entire region. Yeah, more results. So in short, I would like to bring attention to this, what I call human in the loop model creation, which a human was creating new generative models with a natural interface rather than collecting a training set. There are different ways of how a human can be involved in this loop. You can just apply any kinds of editing operations, like what you are using for image editing or video editing. Maybe that could be an operation for model editing as well. It can be sketching, can be blending, but it can be many more. And some recent work from Daniel Cohen's group are also using text to modify the weights of the model, called style nada. So there are different ways of interacting with model. It does not have to be sketching or just copy and paste. And the model does not have to be GANs. It can be diffusion models, can be VAE, so flow-based model, also can be 3D models like NeRF models, can be transformer, can be theorem-based. So there are different models we can interact with, as long as this model produce some visual output, and we like to control the output the model can produce. So the goal is to go beyond this kind of restriction of collecting training data to realize a model which can reflect what we think and what we imagine. By that, I thank you for your attention. Happy to answer any questions. Yeah.
Thank you so much, Yunyan, for the presentation. Maybe it's just time for taking some questions if there is any.
Hello.
Yes, please, Deborah.
Yeah, thank you for this presentation. So I had a question like for the model rewriting part. So it currently kind of works on the output of the GAN write. Like, for example, I was interested in, like, say, a scenario where there's a mountain scenery. The GAN is trained to generate the mountains, and I want to put, let's say, a church in there in that image. Then how will this be possible, or it's kind of not?
Yeah, I think there are two kind of difficulties, as you mentioned, which people are still working on it. One is how to apply it to real images, which involves some GAN inversion, which are also very challenging for generic non-face images. And the second issue is, for example, you have two models, which one model is generating church, the other model is generating mountains. How do you do this cross model editing, which people have, which are still difficult. I think one paper I remember from a hard school in Israel is they have something called model. If I'm not mistaken, it's called model routing. Is you can kind of enforce these two models to share some backbone, like you want, and then maybe it's easier for editing because if the model shares some like weights, so you can look at these papers. Yeah, if you send me email, I can send you the paper. I don't remember the name now. Yeah. There are two challenges. Yeah.
Yep. Thanks.
Okay, thanks again for the presentation. Thanks everyone for attending. Please keep in touch, Yunyan, and have a nice day.
Yeah, thanks for having me. Yeah, thanks everyone for your attention.